All right, so it's now, we are on the hour. So our next speaker of this session is Alex Belin. So please go ahead.
Great, thanks a lot. So I'd like to start by thanking Jeff and the rest of the organizers, of course, for the invitation to speak today, and really also salute their courage and determination in making this conference happening under the current circumstances. On the bright side, there's, I think, over 2,000 participants. This has to be the biggest strings ever, and it's really amazing to see everybody from, basically 24 different time zones tune in at the same time and interact. So it's really been a lot of fun so far. So today, I'll talk about something that I'm really excited about right now, and the talk will be mostly based on a paper that came out a few months ago with Nathan Benjamin at Princeton, Alejandro Castro in Amsterdam, Sarah Harrison at McGill, and Christoph Keller at the University of Arizona. But really, this is sort of the latest in a series of papers that we've been writing in the past couple of years with Alejandro and Christoph, along with Joao Gomes and Beatrix Mühlmann, so I'll also refer to all the results along the way. The main question that I'd like to address today is the following. Oh, now it's not working anymore. Okay, great. So the main question I'd like to address is the following. What is the space of consistent UV-complete theories of quantum gravity? And well, this is very much of an open question for quantum gravity in asymptotically flat space or in de Sitter space. And we just heard earlier today, general principles from Kumrun that should apply to all theories of quantum gravity. Things are much better if you consider instead a negative cosmological constant. And one could say that ADS-CFT has essentially solved this question. And this comes really by considering the strongest form of the ADS-CFT correspondence, which says that the space of theories of quantum gravity in d+1 dimensional anti-de Sitter space is equivalent with the space of conformal field theories in one less dimension, in d dimensions. Or one could put it differently and say that every conformal field theory in d dimension is dual to some theory of quantum gravity in one dimensional higher anti-de Sitter space. And what we mean by that really is the following, is that the local observables of a conformal field theory are the set of local correlation function. And given any local correlation function, you can always interpret it as the amplitude of some scattering process in ADS. Okay, and if you're more used to flat space physics, you can think about this a little bit like the S matrix. Anti-de Sitter space doesn't have an S matrix per se. What replaces it is a set of conformal correlators, but by specifying the conformal correlators, you really fully specify the theory. But of course, a conformal field theory is UV complete and non-perturbatively defined. So you can really think about the conformal field theory as giving a non-perturbative definition of quantum gravity in ADS. Okay, of course, I said the problem is solved. I've been extremely cavalier. And what I meant by it's solved is that we really know what to look for. And what to look for are conformal field theories. Of course, classifying the space of all conformal field theories is the venture of the conformal bootstrap. And even though there's a lot of exciting progress happening right now, we currently have no complete classifications for all CFTs, even in two space-time dimensions where things are very constrained. So that's the first sort of caveat, which is quite major, of course. The second is that if you take a generic CFT, maybe your favorite CFT is the 3 Ising model, or maybe it's the free boson in 4 dimensions, and you start computing correlation functions, what you'll get from that will have nothing to do with what you expected from the classical theory or the semi-classical theory, which should be semi-classical general relativity. So while we can say that the space of all CFTs classifies the space of all theories of quantum gravity in ADS, there's really a subset, and a quite exotic subset of theories that are better. And they have the particularity that if you start looking at the correlation functions, they seem to behave like semi-classical general relativity in one higher dimension. Good. So the general approach that the field has taken over the last few years to try to address this is to organize the search in the following way. It's really to implement a 2-step process. The first step is to ask, well, under which conditions or what are necessary and sufficient conditions that guarantees that the gravity dual of a CFT is well approximated by semi-classical GR at low energies. And in this talk today, I will call such CFTs holographic CFTs. Okay, and step one is really trying to understand what are the defining features of holographic CFTs. Maybe one thing that I just want to emphasize is that the word holographic CFTs is often used in sort of with different meanings. As I said in the previous slides, there's some sense in which all CFTs are holographic, or people might also say that CFT is dual to a semi-classical gravity theory, but that is a string theory with the string scale of order, the ADS scale, would be a holographic CFT. For the purposes of my talk today, I'll call a holographic CFT a CFT whose correlation functions mimic very accurately semi-classical general relativity. Good, and then the second step, once these conditions are identified, is to ask, well, can we construct some, or ideally all such CFTs? And there's a third step that I didn't write here, of course, which is to ask, well, how is the gravitational information encoded in the CFT? There's been also a lot of exciting progress by connecting this to quantum information theory, but I won't have anything to say about that today. And I think it's fair to say that most of the effort over the last couple of years has really been about step one. And there's been beautiful talks by Tom 2 years ago at Strings and Sasha last year on understanding exactly what these conditions are and precisely what they imply. On the other hand, I think there's been much less work about the second step, which is actually trying to construct such conformal field theories. And my talk today will be precisely about this second step. Okay, now what I'll try to convince you by the end of the talk is that I'll present some evidence for a new infinite family of holographic CFTs. Okay, so that's the main goal of the talk, but let me not get ahead of myself and tell you a little bit how I'm going to organize this. So this was my sort of brief introduction. First, what I'd like to do is review what these holographic conditions are and where we currently stand. Then I'll introduce a vast landscape of CFTs, which are known as symmetric product orbifolds. And finally, I'll present this new infinite family of holographic CFTs. Very good. So let me get started. So the first condition on CFTs that we want to impose is, like I said, that gravity is semi-classical, which is often referred to as large N. So how would you diagnose the strength of gravitational interactions? Well, what you would do is compute a 3-point scattering of gravitons, which is the scattering here. And this is roughly proportional to square root of G Newton. Now, the dual statement for such a scattering would be to compute the stress tensor 3-point function. And to not worry about normalization, you could divide by the 2-point function to the power 3/2. Okay, and this quantity here, we're going to call it 1/n. Of course, in the examples of ADS-CFT that we're familiar with, n is usually played by the role of the rank of the gauge group. But from this point of view, you can think about it more abstractly. Okay, and if you want the theory to be semi-classical or weakly coupled, you want n to be a very large number. You want this process to be small. In this talk today, I will focus on ADS-CFT in a particular number of dimensions. I'll focus on ADS-3-CFT2, in which case there's a very universal form of this relation, which was given by Brown and Hanot many years ago, saying that the central charge is equal to 3 times the ADS radius over 2 G Newton. And this really shows you that you should think about N or C as some label for the number of degrees of freedom. So holographic CFTs will always involve conformal field theories that have many degrees of freedom. Good. So the next step is to demand not just that the gravity theory is semi-classical, but we would really like the bulk effective field theory to be given by good approximation by general relativity, which is a local effective field theory. Okay, in particular, we'd like higher derivative corrections to be suppressed. So about a decade ago, Hemskerk, Penedonis, and Polchinski and Sully conjectured that, well, if you want that to be true, then what you need to impose some condition on the spectrum of operators. And in particular, it's natural and large N theories to decompose operators into single trace and multi-trace. And what you should demand is that the conformal dimension of all single trace operators whose spin is greater than 2 should be greater or equal to some, again, abstract quantity that we can call delta gap, which is parametrically larger than 1. Okay, and you should think about delta gap as controlling, for example, stringy corrections. And this was conjectured 10 years ago, and there's been a lot of exciting progress about proving it, at least at the level of the 3-point couplings. And again, I'll refer you to Tom and Sasha's talks from the previous years about that. The next condition is quite natural, is to demand that the entropy of the conformal field theory reproduces the Bekenstein-Hawking formula for black hole entropy. And this condition is known as a sparse spectrum, or sometimes it's called the HKS bounds for Hartman, Keller, and Storker, who derived it. And the condition says that now if you count the total number of operators, that the total number of operators for scaling dimensions smaller than C over 12 should be less or equal than this exponential growth here with coefficient 2 pi. And this is really a beautiful paper, but the outcome is a little bit disappointing, because a theory that has a number of operators that grows exponentially with scaling dimension, well, this is a Hagedorn growth for the spectrum, and it's actually typical of a string theory in ADS with string scale and ADS scale of the same order. So one thing that I would like to emphasize here, it's often said in the literature that large gap and sparse spectrum, they're used interchangeably, but they're really quite different. For this reason, I'm gonna sort of refine this third condition, the HKS bounds, and I'll introduce what's called a bulk locality condition, version 2. And we've been trying to find a name for it. We didn't come up with anything particularly smart, so the best we could come up with was a very sparse spectrum. And the condition is really that the growth of light operators does not grow exponentially with a Hagedorn growth, but really in a sub-exponential fashion. Now, I think these conditions 2 and 3 are pretty known by now, but this condition 4 is maybe a little bit less known, so let me spend a slide motivating it. So bulk locality V2. So if we want the bulk low energy effective field theory to be local, then we expect for any local quantum field theory that the free energy should be extensive. In particular, it means that the free energy of the bulk fields, it could be, say, supergravity on ADS d+1 cross m to the big D minus d+1, where big D would be the total number of bulk spacetime dimensions. We expect this theory to be extensive, so it should give us a free energy that scales like T to the D. Okay, and if you translate that statement at the level of what it means for the density of states, it means that the density of states, or the number of operators, grows in the sub-exponential fashion, and this exponent gamma is given by d-1 over d. Okay, and so demanding that our bulk fields behave as a local quantum field theory is a very natural thing to do. One thing that I should say is that it's currently not known how the large gap condition and this very sparse spectrum, or bulk locality V2, interplay. I think it's a very interesting challenge for the bootstrap, but to the best of my knowledge, it hasn't been addressed yet. Good. So that was the first part of the talk where I just reviewed the conditions. So now let me introduce symmetric product orbifolds. So like I said, I'll be mostly focusing on ADS3 CFT2 in this talk. And for two-dimensional CFTs, there's a sort of very powerful way to create a huge landscape of large N CFTs. And the idea is to start with a seed theory that I'm going to call C, and then take N copies of it. Now, the product theory will have a large central charge because it will just be given by N times the central charge of the seed theory. So if you make N large, you get a large central charge theory. Now, the problem is if you just take N copies, the spectrum will not be sparse at all. But you can notice that there's a huge global symmetry in this theory, which comes from the exchange of all the different copies. And what you can do is you can gauge that symmetry, or in other words, orbifolds, by the action of the permutation group that exchanges all of the copies. Okay, and this gives you a huge landscape of 2D CFTs with large central charge parameterized by the choice of seed theory C. And as I'll make a little bit more explicit later in the talk, the orbifold theory, so the Cn, is completely determined by the seed theory. So if you've solved the seed theory, you know its spectrum, all its correlation functions, and on arbitrary manifolds, then you also know the orbifold theory. And there's other types of constructions that you can do. You can even make this landscape bigger if you, instead of orbifolding by the full symmetric group, consider subgroups, and these are known as permutation orbifolds, but I won't really discuss them in the talk today. Good. So now let me say a little bit about how these symmetric orbifolds play against these holographic conditions that I introduced earlier. And one very nice thing that comes out of the analysis is that the result is completely independent of the choice of the seed theory. And independently of the choice of the seed theory, the following happens. Well, large N, as I said, is built in just by taking the N copies to start with. And the HKS bound, the sparse spectrum, actually is universally satisfied and actually saturated. And this was shown by Christoph a few years ago. So that's really nice. That's already a good start. These theories, for example, will universally reproduce the BTZ black hole entropy. But of course, this immediately presents a puzzle or a problem, because if they saturate the HKS bound, it also means that, well, they don't have a very sparse spectrum. And similarly, they don't have a large gap to higher spin operators. You can check that these theories have a huge number of higher spin currents. And in fact, you should think about them as free discrete gauge theories. Okay, so that looks pretty bad. If you just take this at face value, you might want to say, well, okay, game over. These theories are nice, but they're not the way to go. You're never going to get holographic CFTs from them. Now, if I declared at this point that this was game over, many of you would be, of course, surprised, because the canonical example of ADS3 CFT2 involves precisely a symmetric orbifold, where the choice of the seed theory is the nonlinear sigma model on T4 or K3. Okay, so how is that compatible with everything that I just told you? Well, what happens is that there's a conformal manifold, and really you can take your CFT at the orbifold point and deform it by an exactly marginal operator O, and this new theory is also a CFT. Okay. And really, the orbifold description is just the point where lambda equals to 0. It's the free point, and it's dual in the bulk to tensionless strings. And it was as was very nicely discussed by Rajesh yesterday. So the way you should think about it is the following. At zero coupling, we're at the orbifold points. As Christoph showed, no matter what the choice of the seed theory is, the density of states or the number of operators grows exponentially. And at the same time, the gap to higher spin operators is order 1. And then you turn on this coupling, you take a very large value for it, and most of the operators acquire huge anomalous dimensions. And when you count the number of operators that are left, you only get this much smaller growth, which is e to the delta to the 5/6. Okay, and again, this 5/6 is not an accident. It's really because the gravity dual is ADS3 cross S3, so you're counting 6 space-time dimensions. And at the same time, as you turn on this coupling, and if you study the higher spin operators, they will acquire large anomalous dimensions. And so at large lambda, there will be a large gap, which is much greater than that. Good. So this happens for the choice of the seed theory to be T4 or K3. But there's a very natural question, which is, can we find new examples for other choices of seed theories? And in this talk today, I'm going to focus on two-dimensional conformal field theories with 2,2 supersymmetry. And I'll just do that to organize the search a little bit, which will make things very convenient. Okay, so it's a restriction, but it will be a convenient restriction. And as I said at the beginning, what I want to argue for is a new infinite family where something very similar happens. But first, what I'd like to do is revisit a little bit these holographic conditions for symmetric orbifolds, and tell you a little bit how I'm going to evade the fact that 2 of them failed. Good. So recall that the large N and the sparse spectrum part, that's done. That's already okay at the orbifold point. You don't need to do any more. What we're missing is the large gap to higher spin operators, and we want to transform this sparse spectrum into a very sparse spectrum. Okay, so let's start with the large gap condition. Well, if you want to introduce a large gap, the first thing to require is that there exists an exactly marginal operator in the first place that enables you to move away from the orbifold point and starts giving anomalous dimensions to the higher spin currents. So we want to be able to deform our action by an operator. And this operator is going to have a little bit of structure here coming from the fact that we're in a large N theory. So let me introduce the various terms. The coupling that I turn on is really lambda times this n. And lambda now is an n-independent function. Okay, so I've factored out the n scaling. And the n scaling depends on the type of operator that I want to turn on. If I imagine that my theory has a nice Toth limit, and I want to preserve this Toth limit by turning on the operator, well, I need to specify if the operator is single trace or multi-trace. So k enables the number of traces, and so I need to tune n accordingly to preserve the Toth limit. Now, you can check that if you want this operator. So what are the things that we want from our operator? Well, the first thing is that we want it to be exactly marginal. So we want the conformal dimensions of O to be 1, 1 for H and H bar, and we want it to be protected. So we don't want it to acquire anomalous dimensions under the deformation. The second thing is that, as I said, K is the number of traces, and if you want the operator to be able to give large anomalous dimensions to most operator in the theory, you need the operator to be single trace. So O should be a single trace operator. And finally, if you want to be able to introduce coupling between the n copies, you need O to be in the twisted sector. Very good. So it turns out that exact marginality is not that hard to obtain, and this is thanks to supersymmetry, and it is one of the reasons why it was convenient to study supersymmetric CFTs. If you take a chiral primary operator, which is a half BPS operator, with the conformal weights equal to 1/2, which implies in particular that its charge is 1, potentially -1, then there's a generic way to obtain an exactly marginal operator. You just act on it with G, which is the mode of the supercurrent. Okay, so if you act with G minus 1/2 on this chiral primary of weight 1/2, then this operator's conformal dimension is protected. In other words, you have an exactly marginal operator. Now, I also said that I wanted the operator to be in the twisted sector, and you can look at the weight of the lowest weight operator in a twist L sector. So the lightest chiral primary in a twist L sector. Okay, and it turns out there's a very simple formula for that. It's just C/12 times L minus 1. And this should maybe be contrasted with the usual ground state formula for the twist operators that you might have seen in entanglement entropy, which is C/24 L minus 1/L. By demanding that it's chiral primary, you get a shift and you arrive at the following formula. And if you want this, so if you want to have an operator with dimension 1/2 and L to be greater or equal than 2, this immediately tells you that the seed theory central charge has to be less or equal than 6. Okay, this is already quite restrictive on the choice of seed theories that you can have. And of course, K3 or T4 correspond to C equals to 6. Great. So that was about the existence of a marginal operator. And maybe one thing that I should say is that this condition is not sufficient. It's necessary because you want to be able to move away from the orbifold point. But what you would really like to show is that you give large anomalous dimensions to all operators. And this is not guaranteed by the mere existence of the operator itself. And I'll talk a bit more about this at the very end. Let's turn to the spectrum. As I said, I wanted to improve this Hagedorn growth of light operators to a very sparse spectrum. And so the question is, well, okay, say there is a strong coupling point. What is the growth for the number of operators at strong coupling? Of course, computing that is extremely difficult. So again, I'll use a trick that's possible thanks to supersymmetry. Instead of counting all the operators in the theory, I'll count just the BPS operators. And of course, the total number of operators in the theory has to be greater or equal than just the BPS operators. Now, if you count the BPS operators and you find an exponential growth, well, you're screwed. Game over for real this time. However, if you count the BPS operators and you find this very sparse spectrum, then that's a good start. And just like before for the existence of the marginal operator, it's not sufficient, but it's necessary. So it's at least a good starting point. Okay, and the way that I'll choose to study the number of BPS operators is by studying the elliptic genus, which is the partition function in the Ramon sectors with a -1 to the F inserted. And we're turning on a chemical potential Y, which is e to the 2 pi I z for the U1 current, the U1 charge. Okay, great. So why use the elliptic genus? Well, there's two big advantages. The first is that it's protected on the conformal manifolds. So you can compute it at weak coupling, where it's actually computable, but it's also going to be valid at strong coupling. And so, as was argued by Nathan and his collaborators and Christoph in previous papers, this is a very useful trick because it's a window into a putative strong coupling regime. So you can, compute it at weak coupling, but then if it grows very slowly, it tells you that perhaps there is a strong coupling regime. Very good. The second reason is that the elliptic genus, up to unwrapping, as I'll mention in a second, is a weak Jacobi form. And a weak Jacobi form is a very nice type of modular form that has been studied to death by mathematicians. And it turns out that the space of weak Jacobi forms is a finitely generated ring, or in other words, there's really a finite number of possibilities to explore. Okay, and this should resonate a little bit with the modular bootstrap, is that classifying theories is hard, but classifying their partition functions sometimes can be much easier. And just like for chiral theories, any modular invariant function should be a polynomial of the J function. Well, something sort of similar happens for weak Jacobi forms. You have more than one generator, though. And again, I said that there's a caveat here, which is up to unwrapping. It could happen that the charges are not integer in your 2D CFT. And so you would not get a weak Jacobi form per se, but just by unwrapping the chemical potential, you can turn any elliptic genus into a weak Jacobi form. Great. So, so let me define the following. So I'll take this elliptic genus, perhaps with some unwrapping parameter kappa that will not be too important. This will be a weak Jacobi form. So this is the elliptic genus of the seed theory. This will give me some weak Jacobi form. And I can expand it in Fourier coefficients, which are these C and L's. Now the question is, what is the elliptic genus, or what is the resulting weak Jacobi forms for the symmetric orbifold theories? And it turns out that to find them, it's sort of more convenient to introduce a generating function for the elliptic genera. And this generating function, so what you do is you introduce a chemical potential, P, or P is e to the 2 pi I rho. You introduce a chemical potential for the central charge, and you compute the generating function for the elliptic genera. And this has a really nice formula due to the work of Dijkgraaf, Moore, Verlinde, and Verlinde. And if you spend some time in the Netherlands like I did, you really learn to love and cherish this formula. The resulting formula is very simple for the generating function, sorry. And it's just a simple product formula. And the only place where the choice of seed theory appears is in the exponents here. You get C to the n times m comma L. Okay, so this is a little bit reminiscent of what I was saying before, is that the symmetric orbifolds are completely determined by the choice of the seed. And here, the choice of the seed fixes these coefficients C, which also fixes the elliptic genera for all symmetric orbifolds. Great. So the information somehow about the choice of the seed is encoded in these Fourier coefficients C and L. And maybe it's worth saying that, again, there's a finite number of, it's finitely generated, the space of weak Jacobi forms. So really all you need is a finite number of these C's. Of course, all of this is put together and it's a bit of a mess to extract what you want, which is the growth of the spectrum at large central charge. But after some amount of work, we were able to do it, and we obtained a complete classification, which really means the following, is that you hand me a weak Jacobi form, I will take the symmetric orbifold of that, and what we showed is that there's two possible outcomes. Either the growth of the BPS operators grows exponentially, in which case, really, like I said, this is game over. But in some rare cases, for some sort of finely tuned weak Jacobi forms, you get actually a much slower growth. And you get a growth which is e to the square root of delta. And you might have thought that there could be sort of intermediate regimes with different powers, like 2/3 or 3/4, and it turns out that that never happens. We don't really know why at the moment. And what we give, this complete classification, is we gave a very simple criterion to distinguish these two outcomes based on a finite number of Fourier coefficients of the seed elliptic genus. So the way I like to think about this classification is that, well, yeah, first of all, maybe let me just say one thing. The criterion is a little bit involved to write down. It's not super illuminating, but it does give you one constraint. And the constraint that it gives you, one constraint that's easy to see, and that constraint is that the central charge of the seed theory has to be less or equal to 6. Okay, and that's not all it gives you. There's more involved things. But this is sort of the order 0 constraint that it gives you. Okay, and this is exactly the same as we found for the existence of a marginal operator in the first place. Now, I'd really like to stress that these two conditions are completely independent. They're probing very different things, and it's already quite astonishing that you get the same constraints for both of them. Of course, we hope that there's a physical reason behind. The fact that you have a slow-growing spectrum is because of the existence of a marginal operator. But still, in principle, we could have had different outcomes here, and I find it quite astonishing that you get the same constraint on the seed theory. Good. So how to think about this classification? Well, the way I like to think about it is that it really serves as a map. Of course, given a partition function, there's many different CFTs that could have that same partition function, but it at least tells you where to look. And originally we had found, 4 of these new slow-growing functions, and we thought that there wouldn't be any more, probably. And for that, I'll also refer you to Alejandro's talk last year. But now, with this complete classification, we realize, well, actually, that's not true at all. There's infinitely more. There's an infinite family of these slow-growing functions. And it just so happens that some of them actually already have an illustration in holography. And there's a very nice paper by Dada, Eberhardt, and Gabriel, where they considered orbifolds of T4 by discrete isometry groups. And they studied their elliptic genus, and it just so happens that all their examples can sort of be embedded in our slow-growing functions. So this is already quite nice, but of course now we have infinitely more. So it's natural to ask, well, okay, can we get actually new examples of ADS CFT from this? So the strategy will be the following. We have the partition functions. Now all we need to ask is, well, are there conformal field theories that have these functions as their partition functions? Okay, so we need to look for CFTs that have these sort of slow-growing forms as their elliptic genus. Next, you take these theories and study the spectrum and look whether or not there's exactly marginal twisted sector single trace operators in the symmetric orbifold. If you find that both of them succeed, then I would say that this is pretty strong evidence for new holographic CFTs, with some caveats that I'll come to at the very end. And just for practical reasons, it turns out to be convenient to split the search into two groups or two ranges for the central charge. The first one is to consider central charges between 1 and 3, and the second one between 3 and 6. And the reason for that will become clear in a second. Good. So why split it up? Well, the reason is that there's a complete classifications for all supersymmetric 2D CFTs with central charge between 1 and 3. And these are the n=2 minimal models. So just like for Virasoro minimal models in the bosonic case, there's a complete classification for all CFTs with central charge between 1/2 and 1. Well, there's an equivalent statement with supersymmetry, but now the range is between 1 and 3. And these theories are labeled by an integer, a positive integer k, and the central charge is 3 times k over k plus 2. Again, as I said, for a positive integer k. And it can happen that at a given value of k or at a given central charge, there's more than one way to obtain a modular invariant partition function. So there's really an ADE classification for the n=2 minimal models, and there's the A series, the D series, and then 3 exceptional examples, E6, E7, and E8. Again, this is not crucial for the purposes of this talk, but what is important is that there's a complete classification for all theories. We know them, we know their spectrum, we know their elliptic genus, we know everything we want to know. Okay, so let me come to the main results that I wanted to introduce in this talk, is that if you take the seed theory to be any of the n equals to 2 minimal models, then the following two things happen. The elliptic genus exhibits a slow growth, so we seem to have this very sparse spectrum, and there is at least one exactly marginal single trace twisted sector operator. Okay, and this happens for any choice of n equals to 2 minimal model. So I think this is pretty compelling evidence that there's a new infinite family of holographic CFTs. And you can ask, of course, well, how did you check this? Well, like I said, everything you want to know about the minimal models is known. So you just look at their spectrum. You take the elliptic genus, you run it against our slow growing criterion. You see that it works for all theories. You can do this analytically. And then you do the same thing for the twisted sector operators. You count them, you look if there's chiral primaries with weight 1/2, and you can just check all of this explicitly, as we did in the paper. And of course, I'm going to spare you the details today.
Alex, this is the 5-minute mark.
Perfect. You can also ask what happens between central charge between 3 and 6. And there, well, there was no full classification for all CFTs, but you can consider some examples. One thing that you can do is consider products of minimal models. You can also consider other types of theories, which are the Kazama-Suzuki theories, which are these cosets here. For big M equals to 1, these are just the minimal models, but they have generalizations, and there's some ranges of K and M where the central charge is smaller than 6. So, of course, as I said, there's no full classification. We didn't do an exhaustive search at all, but we did look at some examples, and the following things seem to happen. Well, every time we found a slow-growing elliptic genus, we looked for the marginal operators, and we always found at least one exactly marginal operator. When we wrote the paper, we also thought the converse was true. Since then, we found one counterexample. So, well, I'll give it to you as it is. It seems that the converse isn't true, but that's very much work in progress, and we don't really understand exactly what's happening with this particular counterexample. Very good. But there's a lot more to explore for central charge between 3 and 6. Some interesting properties of the models is that the dimension of the moduli space is growing very fast. And so the theories are much richer than for T4 or K3. They grow extremely fast with K, roughly like the number of partitions. And in particular, there's something that I find really interesting about them is that there's many, like tons of exactly marginal multi-trace operators. And there was really some beautiful papers in the early days of ADS-CFT by Aharoni, Berkuz, and Silverstein, where they talked about how to think about exactly marginal multi-trace operators in ADS-CFT. And they discussed examples where you have double trace operators. Here we have triple trace, quadruple trace. It can go as high as you want, which is of course only possible in D equals to 2. But the way to think about this is that these theories, they will affect your tree level scatterings in the bulk. So it seems that the gravity duals of these theories, if they exist, would have tunable bulk couplings in the Toft limit. And one thing else, another thing that you could try to do with these theories is turn on these triple trace operators, but breaking the Toft limit. And this would give you a way to produce gravity duals that would be strongly coupled ADS matter, but weakly coupled to gravity. And this is also something that I think is becoming pressing in the large N bootstrap. But let's just leave that as a teaser. So I should, of course, say, how could it be that our models are not holographic? Okay, I said I presented evidence, not a proof. Well, it could turn out that they're not holographic if the following two things happen. You could ask, how do the anomalous dimensions grow at large lambda? Okay, and the D1, D5 CFT or n equals to 4, they just grow with some power of lambda. Of course, it's a logical possibility that as you crank up the coupling, well, actually, the anomalous dimensions saturate and stop at some order 1 value. And if this happens, and if at the same time there's miraculous cancellations in the elliptic genus that explains this slow growth, then it could happen that the gravity dual is not truly holographic, but instead would have LADS over L string order 1. The theories would still be chaotic. They would, the coupling would destroy integrability, but these theories then would be more similar to the supersymmetric SYK models in D equals to 2 that were introduced by Mergen, Stanford, and Witten. And I think this begs for an interesting large and gauge theory question, which is take a CFT with a 't Hooft coupling and an exactly marginal operator, which you can interpret as a gauge coupling. And let's define some type of critical exponent such that at large lambda, the anomalous dimensions scale like lambda to the beta. When can you know under which conditions are you guaranteed that beta is positive? So this is a bit the reverse logic of what people were obsessed about in the early days of ADS-CFT, which were non-renormalization theorems, making sure that some operators remain there. Now we can, somehow the question is, can you make sure that all the operators that acquire anomalous dimensions acquire ones that are arbitrarily large? And of course, this can only happen because of large n. That's what opens the window. Otherwise, like S-duality would screw you. So I think this is an interesting sort of more abstract large and gauge theory question, and I'd be very interested to hear your thoughts about it. So I'm basically out of time. So this is my last slide. So if the 1 minute warning comes, it's fine. So I presented today evidence for a new infinite family of holographic CFTs. The theories are obtained by taking the symmetric orbifold of any of the n equals to 2 minimum models and deforming away from the symmetric orbifold point with twisted sector operators. The theories have really interesting moduli spaces. Everything's much richer than D1, D5. And of course, the natural questions that you're going to ask is, well, what is the supergravity background? We don't know. We have the explicit form of the BPS spectrum, so maybe somebody might recognize it. Perhaps more ambitiously, can we find top-down derivations with some brane constructions in string theory? That would be, of course, amazing. And finally, there's this more abstract gauge theory question. Is there some kind of renormalization theorem that you can prove? How would you prove it with integrability, localization? I don't know. But again, I'd be interested to hear your thoughts. With that, I'll thank you very much for your attention.
All right, thanks a lot. So let's move on to the questions. So the first question will be by Edward Witten. Please go ahead.
Assuming that you do have holographic or bulk semi-classical bulk dual descriptions because your anomalous dimensions are big, can you at least tell us in what dimension are those bulk descriptions? So in other words, for the symmetric orbifold of T4 or K3, the answer is that the bulk dual is 6-dimensional, ADS3 times S3. Do you know the analog of the dimension of the S3?
No, that's an excellent question and something that unfortunately I didn't have the time to discuss. So the problem is, you see, the elliptic genus gives you this e to the square root delta, which might make you want to say, oh, it's in 2 space-time dimensions, but we know that's not true. It's just an artifact of the fact that you're computing an index. So RD for K3, you get this square root growth here, and you can ask, how would I have known that for K3, even for K3, that the bulk is 6-dimensional? And I really don't know from first principles. One would need something like integrability, I think, to try to count the number of operators that remain light. But this is out of reach for now with the current techniques. I should say, again, even for K3.
Well, in the case of K3, you count the half BPS operators. The half BPS might be more than is counted in the elliptic genus. Is there a restricted class of operators you could be counting?
Yeah, I think if you count just half BPS operators, then you get a slow growth. You need to count much more than that. You need to count the quarter BPS ones as well, and you don't know which ones are lifted or not. And
it seems to me that in symmetric product of K4 or T4 or K3, if you count the half BPS operators, you do learn that there are 3 hidden dimensions.
Well, as far as I know, there's no CFT calculation of this. One thing that Nathan did is compute from supergravity the quarter BPS operators that you have in supergravity, and then he got a 3/4 growth. But there was no way to, well, it was not clear how to get the 5/6. And certainly, if just from a CFT argument, I think if you count half BPS operators, you're gonna get this growth here. There's just not enough of them, even if you count them without signs, as far as I understand.
You must be making a mistake, because I thought that sort of any one particle state in ADS3 times S3 is half BPS. So you'd be counting the one particle states, which would be sensitive to the dimension of the S3. Perhaps there's something wrong with my reasoning.
I think your reasoning is correct. Is that he wanted to have a formula, counting in terms of some index, but I think it's true they don't contribute to the index. But if you look at the representations and you do more complete analysis, you find that you find this dimension 6 picture.
So perhaps that could be imitated for these theories.
But sorry, Juan, are you saying that there's a CFT counting that you can do that gives you the 5, 6?
Yeah, well, first you count the single particle states, as Ed was saying, and their representations, and they include all the 6-dimensional massless supergravity modes, right?
Yeah, and then you second quantize that.
And then you say that their interactions are weak, so then you just do, yeah.
Even before you second quantize it, when you've found them, the rate at which their mass grows is a measure of the fact that there are 3 compact dimensions.
Yes, of course. Yeah.
Right. Well, yeah. Well, okay. So maybe I'm confusing myself about something, but I thought that somehow I thought that quarter BPS states were important as well, and those are the ones you don't know which ones stay and which ones go at large coupling, and that you really needed those to get to see the 5, 6. But okay, maybe I'm confusing myself.
I don't know. It might be you need some technique other than an index to count the half BPS states, but it might be that you know enough about your very specific theory that you could count them.
No, absolutely, you do know exactly. I mean, you have the the thing that generates the chiral ring, so you could just take the orbifold of that and count all of them, I think. So, yeah, that's how we look for marginal operators in the first place.
Do we know that all those half BPS states persist?
Yeah, I think they can't be touched. Those cannot be touched. Yeah.
In that case, one should be able to learn something from that.
Yeah. Okay. I'll have to think about that. Yeah.
Nice talk. Thank you.
Thanks.
So Kunrum Wafa, please go ahead.
Yes. Thanks for the nice talk. I had a question. So if you take C2 and mod out by ADE subgroups of SU2, you get a theory which is described by a conformal theory of the minimal ADE type, tensored with the Liouville dilaton kind of field, which is makes up the rest of the central charge. So, but the guts of it is that minimal ADE piece. So I wonder if you consider the holography in the context of probing strings in R6 times C2 mod out by ADE, and trying to get ADS3 times S3 times C2 mod gamma, would you possibly get a relation to what kind of models you're finding? Of course, this would entail understanding the extra missing piece in your language, but it seems like it's so close to what you have that may be related to it.
So let me try to understand. If you had an ADS3 cross S3, then you would probably have a bigger R symmetry than what we have, right? You'd have SU2 cross SU2. We only have U1 cross U1, so so I think you would need to consider something more like a squashed S3. Would that?
Or perhaps the opposite question to you would be the opposite, namely start with what I said as a construction. That should exist for sure. And try to see what's the relation of that to the limit you're saying. Maybe there's a deformation of what I just said, which relates to what your model is. It seems like it's so close to your model. It should be related to it.
It could be that those are related to these orbifolds of T4. I don't know. I don't know if Matthias, Struvik, and Lawrence discussed the brain construction for that or anything like that. But they have like Z2 orbifolds of T4. So,
well, in this case, you don't even need T4. I'm just taking the flat space C2. I mean, non-compact space C2.
Oh, I see. Yeah, that's a good point. Oh, maybe one comment that I can make is that I always assume that the elliptic genus does not vanish. So if for some reason in your theory the elliptic genus vanishes, like it does.
No, it won't vanish. It has been computed. It doesn't vanish.
It doesn't vanish. I see. So okay, that's super interesting. Maybe so we have some missing. There's a table that I'm not sure I put in my backup slides with some missing question marks. Maybe that's the theory that you just mentioned. Yeah.
Yes. It's been studied by many people, including Iguchi et al. For the elliptic genus and so on.
Okay, amazing. Yeah, thanks.
So Daniel Harlow, please.
Hey, yeah, so these conditions you've been using to identify holographic CFTs kind of make the most sense if you're in a situation where all the interactions in the bulk are just as weak as gravity is. Do you have, for example, a large N factorization of correlators or having a gap to higher spin? Do you have any thoughts about, from a CFT point of view, what a more general set of conditions could be that would allow interesting particle physics in the bulk?
In the bulk, yeah, I'm really glad you asked that question for two reasons. One is that, as I said, our theories can actually do that. Say the gravity dual exists, then you can deform by this triple trace operator. Where was that? Yeah, you can deform by the triple trace operator and turn on strong interactions in the bulk, even though gravity is weakly coupled to the matter.
But don't you have to make, like, to have it be, can you turn it on with the coefficient that grows with n though?
Yeah, you have to change the power of n. That's the whole point.
But you can do that and maintain.
Yeah, sure. It's exactly marginal at finite n. So you put whatever power you want. Of course, if you wanted to, so you see, this is the scaling that preserves the TOF limit. But if you want to destroy it, you're free to do that. And just to come back to the first part of your question, this is why I like this very sparse spectrum a bit more than large gap, even though I think large gap is on much more solid ground at this point. But large gap really makes sense when you can separate between single trace and multi-trace operators. And if the bulk is strongly interacting, you cannot do that. This bulk locality V2, I expect it to be true in all cases. Even when the bulk is strongly interacting, I expect its free energy to scale this way. Now, the problem is that this condition is on less solid footing. It's not really clear how necessary it is, but it's kind of what we have right now. Yeah.
Thanks.
Guru Lashmi Subramanian, please go ahead.
Yeah, thanks for the nice talk. So in the analysis that we have considered the BPS states, right? Like the number, we said that the rho BPS has to be greater than, so it has to be approximately exponential of square root of the scaling dimension.
Yeah.
But we didn't actually consider the total, like, rho of delta, right? The very sparse condition has been determined by the rho of delta, right? It's not just the BPS, and that has to be greater than the BPS case.
Right.
So does that still, like, so after, is there any direct possibility of computing this rho of delta instead of just the BPS case?
No, it's extremely hard. Yeah, so we'd love to be able to compute rho of delta. So where was this? We'd love to be able to compute rho of delta, but we of course don't know how to. And I think even with the state of the art in n equals to 4, I'm not sure you can, even with integrability, I'm not sure to what extent you can really compute rho of delta precisely. You might want to try to compute rho of delta as a function of lambda or something like that. And even with integrability, that's extremely difficult. So this is why I said that, what I'm introducing here is a necessary condition, but it's not sufficient, because it's a logical possibility. It could happen that the number of BPS states grows very slowly, or what you extract from the elliptic genus grows very slowly, but that even if this grows slowly, the full density of states still grows exponentially.
Right.
And that would be what happens in this situation here for the yellow curve. If such a situation happens, that's what you would see. So of course, we don't know, and this cannot really be checked in perturbation theory. You have to go to strong coupling, and yeah. So
in that case, there could not be like infinitely many holographic CFTs, that you described here.
Sorry, can you ask that question again?
Sorry. So in this case, you've just described that there could be infinitely many holographic CFTs.
Yeah. Oh, sure. Yeah. So it's possible. It's like I said, this is evidence. It's not a proof. So it's possible that none of the theories I introduced work. It's possible that half of them work, or that maybe there's one new one. We really don't know. They all share the same features. So we would hope that whether you land on the yellow curve or the blue curve does not depend on the choice of minimal model, and it really works for all of them.
Right.
But at this point, we don't know. Yeah.
Okay. Thank you.
Thanks.
All right, so looks like there are no further questions for Alex, so let's thank him.